now that we've finished our study on the states of matter and specifically focusing in on gases, we're going to shift our focus to a new unit about solutions. And solutions are mixtures made of dissolved particles in a liquid. So it's kind of a combo sample of matter of a liquid and a solid, but the solid becomes kind of part of the liquid as it dissolves back into kind of its ions. And we're going to talk about the process of solubility in this video, what parts are in a solution, and then what makes something soluble or insoluble. So the first term we have here is solution. This is a mixture made of dissolved particles and a liquid. Within the solution, we call the dissolved particles and the liquid two different terms when we're discussing them. The first is solute. Those are the dissolved particles, so whatever it is that has been dissolved is the solute. For example, in salt water, the solute would be the salt because that is the substance that has been dissolved in the solution. The solvent is the dissolving liquid. Usually it's water because water is readily available and dissolves many things, but you can also have other liquids that are acting as the dissolver in a solution. So again, solute are the particles dissolved and solvent is the liquid that is doing the dissolving. So with that being said, let's look at this table. It tells us to identify the solute and solvent in each solution that is pictured. Let's do some of these together and then you can finish the rest of them out. The first one, it looks like we have some sort of drink mix, so that would be our solute. Could be Kool-Aid or something like that. And the solvent, it looks like this is being dissolved in water. So our solute is the drink mix, that's our substance being dissolved, and our dissolving liquid is water. Next, it looks like we have kind of lots of things going on here. We have a cup of coffee, and then we also have milk and sugar that are being added to our coffee. So this solution has kind of multiple solutes and multiple solvents because we have to also take into account the coffee that's already in the cup. So if we have the coffee, that in itself is a solution, with the solute being the coffee grounds. And when you make coffee, you put that in water. So we have our coffee grounds and our water. There's the first solution. But then we've also added sugar. There's another solute. And we've added milk. So this one has a couple of solutes and a couple of solvents that are working in this mixture. Next, we have a cup of tea. And so our tea leaves are being dissolved. And our solvent is water. Typically that's what you would use for tea, is water. The next one has the liquid actually labeled, so if it's not labeled you can assume that it's water like we've been doing. So our solvent is this liquid ethanol, and then it has a zoomed in picture of all the tiny little dissolved particles, NaOH or sodium hydroxide. So there's our solute. Let's do one more together. Let's do G. So we've got nail polish on the fingers, and it looks like we've got nail polish remover, which is acetone. That's the chemical name of nail polish remover. So on this cotton ball or cotton swab, this has made a solution by dissolving your nail polish off of your fingers. So our dissolved particles now, that would be the nail polish itself, and the solvent would be acetone. I will let you do E, F, and H on your own. Now, let's take a moment down at these other two pictures just to talk a little bit about what happens in solutions when they dissolve. And so we've talked about solvents, that's our liquid, and solute, that's our product, or not our product, our compound that has been dissolved. And so if we look at this picture that asks us to describe how water dissolves a salt, you can see water here on the left, and it's showing the charge separation. If you remember when we show bond dipoles and we draw the arrows to show that separation of charge of where the electrons are pulled, water is, if you remember, polar. And polarity is a driving factor in solubility and how things dissolve, because this separation of charge then is used to pull apart the individual particles of the solute. So here's our solute. I am putting it in a box, and for the sake of exercise, let's just say this is sodium chloride, and we know that the ions of sodium and chlorine are positive one and negative one. Going back to what makes up sodium chloride. In our solute, sodium and chlorine are both surrounded by the polar water, and the side that is negative, which is the oxygen side, attracts the positive sodium. And the positive side of our water attracts the negative side of the salt, which is chlorine. And so as you can see in this second half of the picture at the bottom, we get this dissociated sodium chloride into just the positive and the negative attached to the water itself. And so as particles dissolve in water specifically, they are being pulled apart from one another. And so we call this dissociation of ions. And that is how solubility happens. And you can tell this would probably not work if my salt was not polar. If it didn't have a positive end and a negative end, it would not be attracted to the water. And so we have a little rule that we kind of like to go by called like dissolves like, that polar things will dissolve polar things, and vice versa, nonpolar will dissolve nonpolar. And so when we're working with dissolving, we want to consider the polarity and then ask ourselves, is this a like dissolves like situation? Will it dissolve? So that actually applies for page, I want to say 8. Yeah, page 8, like dissolves like. So in this activity, we just did water. We already analyzed it, showing that this is polar, and reviewing polarity for carbon tetrachloride. Remember, if the arrows balance out, which this one has up and down and side, this is nonpolar. So for the exercises on this page, you are identifying the polarity of these 10 solutes and then deciding which solvent they would dissolve best in, water or carbon tetrachloride, based on their polarity. So you'll need to use kind of that idea of bond dipoles and electronegativity to determine which solvent they will best be dissolved in. So I noticed there's no directions here, so that's what this page is intended for. Now let's go and finish our boxes here at the top in our notes. So we talked a little bit about polarity, and this is a review term. Remember that it's the separation of charge, and we just described how it is kind of the driving factor in the dissolving process. And that is where we get this rule that like dissolves like. And that means that polar things dissolve polar things, and nonpolar things dissolve nonpolar things. And that leads us to these two terms of soluble and insoluble. If something is able to be dissolved, it is soluble, and especially in water, we have described these soluble solutes in water as an aqueous solution. We've talked about that in a reactions unit if it's dissolved in water. When a solid dissolves, it breaks apart into its ions like we showed below. And because of those free-flowing ions, now there's the ability for electricity to go throughout the solution. And so we call this an electrolyte because this solution conducts electricity due to free-flowing ions. If we have a free flow of ions, then we can conduct electricity. If we don't have a free flow of ions, meaning it does not dissociate or it's insoluble, it's not able to be dissolved, then it is a non-electrolyte. And remember, we note that as S. Even if it's in water, it's still noted as just a plain old solid. And so in an insoluble solution, even if, just like I said, if they're placed in water, they're not considered in solution. They're denoted as S, still solid. And they would be non-electrolytes because they do not conduct electricity as a result of them not dissociating or not dissolving. So that takes us down to our last picture here. It says label the solutions as strong, weak, or non-electrolytes and explain your answers. So the biggest thing we want to look for when we're detecting electrolytes, actually there are two things. We want to look at the light bulb. If it is lit, then it's an electrolyte. So we've got two that are lit here. We've got one that's kind of dim and one that's bright. The dim one we would consider weak, and the bright one we would consider strong. The second reason, or kind of the particle level reason that this occurs, is because of the dissociation of the ions. If you look at the picture, it's showing us that in the middle picture that we just called strong, it has completely dissociated and you only see positive and negative charged ions that are freely flowing to kind of these plates on the sides conducting the electricity through the wire. So because of its full dissociation, it has strong electricity. So we would call this a strong electrolyte because it is fully dissociated. Our weak one is because it's only partially dissociated, and you can see that because we have some compounds that have not broken apart, but others that are dissociated into their ions. And then our non-electrolyte has only compounds that did not dissociate at all. So there are our three different types of electrolytes. Use what we talked about to draw solutions, 1, 2, 3, and use those electrolyte ideas to help you draw them. It'll tell you if it conducts electricity or not, and then you can decide what type of dissociation, if it's complete, partial, or not any at all in your drawings. 4, 5, 6, and 7, you'll be able to complete after you watch part 2 of these notes.